Institut Lothair, we will speak about Doubloon, a combinatorial model for a Q extension of trigonometric functions. We're gonna, as usual, we're gonna take Dominique for dinner at 6:45 at the Evening Restaurant. If you'd like to join us, please let me know immediately after the talk. You're all welcome. If you stay throughout the talk and don't use your laptop to check email, then you're welcome to come.
Yes, I have to check my email.
Thank you. So I'll do my best to make it in 49 minutes. So this is the title of my talk. So I'm very pleased to be back at Strasbourg after a few years and to meet so many people who should be already gone for vacation. So the title is this. I have to explain what the Doubloon is. So this is the first thing I'd like to explain. And Doubloon, it was an old Spanish coin used about 300 years ago. And so here we have used it because we needed something to emphasize the double something. And dimer has it been used in mathematics, particularly in statistical mechanics. So finally we found this doubloon instead of doublet to explain what. So first of all, this is based on those three papers, but I'm not going to cover those three papers. I'm going to lecture essentially on the first two. And and first of all, this is summary of the talks. So we explain at length what the Doubloon is, why we have introduced this concept, and then instead of working with the classical major index, I will introduce a second index, which is a compressed major index. Then I will speak on the Q analog of tangent. Tangent, I'm going to repeat what tangent number is, and what a Q tangent means if it had existed in mathematics already. And so next, that's quite much. I don't know if I'm going to cover all this. To discuss the Doubloon polynomial triangle, because it's a triangle of polynomials, and special value of those polynomials refer to classical triangles that have been studied by people before. The Pupa recurrence. Pupa was a nice lady who discovered the Pupa triangle. She did not call it like this, but we did. And so it's a very nice paper written in French, very modestly, but there is a lot of content in it. And I will finish with open questions, so you have talented people who could probably say something about things we cannot solve. So I'd be very happy if this could be done by a young generation. So, okay, let's start the subject. So, Doubloon, I'm very sorry, something very simple. First of all, we have the sequence 0, 1, and 2, 2, n plus 1. So, even number of integers. I start with 0, I end with 2n plus 1. And instead of writing a permutation as a linear word, we write it as a matrix with 2 rows, and then you see how it works. You write the permutation like this: A0, A1, An, and we continue this way: A0, A1, An, Bn, Bn plus 1, B0. That's not a big deal. You see what's okay still, but this is to emphasize the fact that now we have to study the interaction between the first entry and the leftmost and the rightmost, the second one and the next to the last, and so on. So we are going now to define, you see, it's writing like this. We are going to define a group acting on those permutations by rows independently. Okay, so this, a Doubloon, is simply a permutation written as a 2-row matrix. But of course, you know, of course we need an even number of integers, and I take the integers from 0 up to 2n plus 1.
So you take a permutation and fold it.
Yes, exactly. Take permutation and fold it. Good. I think better expression. And fold it. And now, as soon as we have this, there is a natural definition we can make. So how two successive columns behave. And if we have two successive columns like AK minus 1, BK minus 1, AK, BK, those four integers are distinct. So we have four integers, so there are 24 possible ways of ordering them. And so we would say we first define this concept of interlaced or interlacedness. And we would say that this doubloon is interlaced at K if exactly one among AK or BK lies between the previous one. So either we have this between those two integers or BK between those two integers. So now.
This is when we say between, taking natural order into account.
Yes, very good. Between the natural order. Now, first exercise. In a current manner. So there are 24 possibilities I explained before to write for integers. And so now it's interesting K if, okay, now that's important to know this. If AK minus 1, AK, BK minus 1, BK, in that order, like a Z, if this sequence or any of these three cyclic rearrangements is decreasing or increasing. Okay? So it makes 4 plus 4, 8 possibilities. So, well, it's not too difficult to prove this. So this is banal, but you know, it's we have to use the two definitions. Now, okay, all right. I repeat. The doubloon will be interlaced. Let's take this definition. If AK minus 1, AK, BK minus 1, BK, or one of its three cyclic rearrangements is strictly increasing or strictly decreasing. We are going to see an example in a few moments. And the next concept is normalize. You know, surprisingly enough, we need those two concepts. Now, if that sequence I mentioned before, AK minus 1, AK, BK minus 1, BK, is strictly decreasing, then we say it's normalized. So obviously, each normalized doubloon is then also interlaced. So let's illustrate this with an example. That's the only definition I'm going to give, because you see it's difficult to swallow so many definitions. Take this doubloon like this, double, 0, 2, 4, 3, 5, 7, 1, 6, to have an example. Okay, now it is interlaced at 1 because, you see, because 2 is between 0 and 5, you see, but not 7. One of them. Okay, or the other possibility would be 0, 2, 5, 7 is increasing. So it's okay. So it is interlaced in here. Now, now at 2, you have 4, which is between 2 and 7, but not 1. And finally, 3 is between 1 and 4, but this one is even normalized. Because the cyclic rearrangement 6, 4, 3, 1 is decreasing. So in here we have a doublet which is interlaced at 1, interlaced at 2, and normalized at 3. Okay, what do we do?